So here we go. As we all know, and we have talked a little bit about this among ourselves, there has been a star that has been in the news quite a lot lately. Guess which one that one is? It is a very bright one, very easy to find star, which we all call, well, I'm not really sure I should pronounce it yet. So let's go ahead and let's see. First of all, what's the star? How do we pronounce the thing? It's a very bright one, very easy to see. Well, there's kind of two options for doing that. So this is the one that everyone knows.
Beetlejuice. Beetlejuice. Beetlejuice.
Okay, everybody knows that one. However, back in some of us in our younger days, we actually had a little bit of a different option. And in fact, this was the way I pronounced it up until the time the movie came out. And so this is that one.
It's not just some treasure. Old Billy Bones came from Betelgeuse. And you can bet no Betelgeusean is going to settle for no second-class treasure.
Okay, so that's the way I always pronounced it. Never sure that the pronunciation was correct, but heck, what can I say? Who am I to argue with a space pirate? So I always used to pronounce it. I did kind of drop the long E, so I always pronounced it Betelgeuse. So as far as I'm concerned, you can either pronounce it the way everybody does nowadays, Beetlejuice, or the old style Betelgeuse. I will accept the definition either way. So now let's go ahead and get into the nut. This is a star Betelgeuse, as most of us know, and for those of you who don't, this is located in the constellation of Orion. Easy to find. If you can see my screen here, I have the star Betelgeuse marked with an arrow. Take a look at Orion. Here, of course, is the belt of Orion. The star Rigel, which Kent, if you any of you heard Kent and Aurora's presentation Saturday, he talked a little bit about Rigel here being a nice looking binary star. Then, of course, you have everybody's favorite nebula, Messier 42 here, the belt stars, and then we have the star we're talking about here. It is a very red star. However, if you follow variable stars like I do, even at a glance back in January, I could tell that the star was not as bright as it usually was. Tinge seemed to be about the same, but it was not brighter. So let's take a little closer look at this star and let's look at some of the characteristics of this star. Well, here we go. The first is the mass is estimated at roughly, and these are ballpark numbers, 20 suns. But there's a lot of uncertainty on this star. I have actually seen measurements of this star ranging from 25 stellar masses down to about 15 or 16. You know, that's a pretty large uncertainty. And the reason for that's pretty simple. The easiest and most direct way we have of measuring the mass of something like a star is if there's something orbited. In the case of the sun, it's easy. We have planets. In the case of binary stars, you have one sun orbiting the other, so it's fairly straightforward once you have determined an orbit to determine the masses of the stars. Betelgeuse, insofar as we know, is a single star. There have been some claims that there's a couple of companion stars to it, but that has so far not been demonstrated to any kind of certainty. So we're going to kind of stay with about 20 suns, but understanding there's a lot of uncertainty. So how bright is it? Well, given how given how big it is, mass of about 20 suns, this is a very, very bright star. Current estimates again are it's about 100,000 suns, but again, if we don't know exactly the mass of the star, we're not also, it's going to have a difficult time figuring out exactly what the luminosity. If the star were, say, 25 suns, then it would be somewhat more luminous than it is here. So there's some more uncertainties here. So what kind of class is it? Well, the star is classified as a class M1 to M2, and their reason that you have both the M1 and M2 is that as Betelgeuse varies in its brightness, it also varies in temperature and color slightly, so it'll go from an M1 to an M2. Now, these classifications are basically based on the stellar spectra, basically what they're made out of. These stars are cool enough that you actually can have molecular compounds form in their atmospheres. And so they'll absorb a little bit of the light, and we identify them. One of the characteristics of these M-class stars is that you have a titanium oxide. So just as incidentally, going back to Dr. Field's talk, Betelgeuse hasn't produced titanium yet. So therefore, any titanium that we're seeing in its atmosphere had to have been there when it's formed. So a star kind of like Betelgeuse simply could not exist in the early part of the universe. So that's the M1, M2 stars. The 1A, B, and B, all that really means is that this is a astronomer's classification of basically a type of star. Betelgeuse is a type 1. It is a supergiant, and I mean supergiant. It is a very big star, and we will be getting into that in a minute. And so now we come to the next part of it. Well, how hot is a star? Well, the sun is about 5,800 K. Kind of think of that as around 10,000 degrees Fahrenheit. And the surface temperature of Betelgeuse appears to be about 3,500 K. However, there are uncertainties there. And why? Well, any body, for example, like the sun, you have what's called a black body. It actually radiates through most of the spectrum, and it'll peak at a certain point in the spectra, depending on how hot it is. However, when you have these very, very cool stars, those molecular compounds I will talk about, a lot of those spectral bands that you see will literally block out a lot of the blue light. So you don't really have a whole lot of blue to really get a good idea about the blue part of the spectrum. So you kind of have to use models and physics, and you kind of have to infer what the actual temperature. Well, naturally, all of this type of stuff introduces uncertainty. So now for the final one, well, what's the distance? Oh, about 670 light years, although, oh boy, here we go again. We got some more uncertainty in here. The actual uncertainty is actually a pretty good amount. The last estimates that I saw, which I checked up on a couple of days ago, was you have a plus or minus 134 in the light year, so it could actually be a little bit closer. Well, guess what happens to the luminosity of the star if it's closer? Well, the apparent brightness gets brighter, but the actual brightness of the star goes down. If it's further away, then of course the star will appear dimmer, but that also means when you calculate its actual luminosity, it's going to go larger. So this introduces more uncertainty into what we think the brightness are. So now let's go into, well, how big is this thing? This is the scale of the solar system. The outer circle here is the planet Saturn and Jupiter, and you can see the star appears to be roughly about the size of Jupiter's orbit. That is one big star. You can also see that it appears to be a little bit misshapen. With stars this big, gravity can be pretty weak at a surface, so the material on it is not really held all that strongly, which means that it can also lose it fairly readily. And in a lot of red stars, we see them surrounded by dust that they have indeed ejected from them. So now let's get to the nub of the thing. Here is what the star Betelgeuse has been doing for the last year. I want to draw your attention first to this part in the center. These are basically the black dots are the visual estimates. And you can see that the variation here is pretty small, but it's very definite from year to year. Now let's go to what it's done on this last cycle. You can see that the minimum here was actually, it occurred in January, was actually quite deep. It was actually something almost 3/4 of a magnitude dimmer than it usually is. So this led people to speculate that the star might be about to turn into a supernova. I was somewhat skeptical of that assessment simply because it doesn't match what I understand about the evolution of stars. So I decided that I was going to go look at the history of the star to see what else is done. So now we're going to go back 50 years. This is measurements from an organization I belong to, the American Association of Variable Star Observers. So you can see that there appears to be kind of a semi-periodic variation that Betelgeuse goes through every year. You saw that in the previous slide. But let's go back to the year 1985, which is right around this area here. Is that coming from me? I hear a lot of noise in the background there. Okay. So you can see that we actually had a similar thing back in 1985. Now, that wasn't as deep as the one we experienced this year, but it lasted. It looks like that minimum lasted for about 3 cycles. So this is not actually something that is unique to this particular star. It has been seen before. Well, now I get curious, so I decided to go back even further. So now let's go back 100 years. I kind of stopped at about the year 1920, because the data starts to get pretty sparse and it's kind of difficult to draw any reasonable conclusions. Well, as you can see, going back this, it appears to have done that a number of times. But what I wanted to bring your attention here is, let's take a look at this right here that occurred about the year 1937 to the early 1940s. Here, we had a little bit of a minimum that was deeper than usual, but also look at this, we had a maximum brightness that was dimmer than usual. So I can imagine that that if we had known about the nature of supernova then as we do now, I can imagine us having this very same discussion on whether Betelgeuse was about to blow up into a supernova in 1940. So as you can see, Betelgeuse has kind of had an interesting history. So the behavior it's in, although deeper than normal, is not all that unusual. So now let's go and let's look at a comparison. Let's look at the star itself. What I want to show you now is some of the convection that is occurring in some of these stars. Now, this particular slide you have now, this is the sun, and I want to show you, this is convection on the sun. Okay? And so I want you to look at these individual convection cells. These on the sun are roughly about the size of Texas. Okay? Pretty good size, but as the sun goes, not all that big. Remember, the sun's about 860,000 miles across. Now, let's go to, this is a model of the expected convection activity that we would see on a star like Betelgeuse. So now let's take a look at this one. So take a look at those convection cells, and I'll run this through a couple of times. Remember that we're talking about a star that is the size of Jupiter's orbit. So how large are these individual convection cells? Well, we're talking about orbit-sized convection cells here. And I want you to look again at the pattern of bright and dark. You'll notice that you'll have cool material and you'll have brighter material, and you will see that you see some variations in it. Normally, these kind of smooth themselves out, but occasionally you can get something build up, say, for example, the equivalent of 2 wave crests coinciding, or in this case, 2 trolls coinciding. So when that happens, we would expect some of the points of brightness and the points of minimum magnitude to kind of coalesce. So let's see if there's any evidence that this is actually occurring. These are images that were taken of Betelgeuse last year. Betelgeuse is unique in that it's big enough and close enough that the star is not a direct pinpoint, but that it actually has a size. So this one was taken in January of last year. This was taken in December during the dimming. You'll notice the contrast between these two basic hemispheres. You kind of have that continued bright spot here, but notice what we have here at the lower right. What have, say, for example, a dark cell, or possibly just a kind of super huge star spot that is participating in the dimming of the star. So that's kind of what we think has been going on now. So let's kind of look at the star again at some data on the star itself. You saw a variation on this in Dr. Field's presentation. This is the basic structure of a star that's about to go supernova. So here's the various shells, hydrogen fusing. Now, these diagrams are a little bit misleading because it kind of shows these shells as fusion sites, which they are, but the entire shell is actually not fusing. So what's happening, like I will use this one as an example, between the hydrogen shell and the helium, there'll be a shell of fusing hydrogen, but then there'll be basically a shell of hydrogen ash, and here at the inner end of the shell is actually where the helium fusion would be occurring in a shell. Now notice that this will occur after helium burning has already occurred in the core and it has run out. And one of the consequences of these shells is that very often what you see on the surface of the star does not necessarily coincide with what is happening in the core of the star, but more in the energy production in these outer shells, because these outer shells will very often actually produce more energy than the fusion in the core. So now let's go in and see about the time scales. You saw a similar table like this in Dr. Field's presentation. Now we're using a 25 mass star. This is kind of at the upper end of the estimates I've seen for Betelgeuse, but you'll notice hydrogen burning has only occurred for about 7 million years. But take a look at these time scales. You'll notice how they get shorter. Carbon burning 600 years, neon burning 1 year, oxygen 6, and silicon burning into the iron group only takes a day. So this kind of gets into the question of how close we actually think that Betelgeuse might be to actually exploding. You hear these variations that, well, it might take up to 1 million years, and that is, where in this cycle do we actually think Betelgeuse's is? If it's, say, for example, is in between carbon and neon burning, it's not very long. But if it's in one of these other stages, it's not. So let's go ahead and take a look at this, the evolution of stars. Now, this is a variation on one of the astronomer's primary tools. It is what we call the HR diagram, and it's basically a plot of the star's temperature versus the luminosity of the star. The ones we're looking at here is the 20 mass star that we're looking at here. This stage over in the left is still in the hydrogen burning stage, and it's that part that takes about 7 million years. And as it gets over here, notice these loops over at this end here. These blue loops occur when the star starts burning a new nuclear force in the core, because the star will then contract and it will heat up and it will then kind of move blue. So every time you see something like this moving to the left, you'll see a new fuel. So where in this process is Betelgeuse? Well, you'll notice that we saw the temperature of about 3,500, and that we estimated that it was about a 20 mass star. Luminosity of about 100,000 suns. That would put it on right about the 5 here, because this is a logarithmic scale. Well, that would actually put where we measured Betelgeuse. Oh, that kind of puts it right about here. That's kind of doesn't really correspond to this. So one of my interpretations of this is that potentially Betelgeuse might be somewhat less than 20, but remember what I said. There is a lot of uncertainty in all the measurements, the mass, the luminosity, the temperature, and that will all affect on exactly where on the the precise location on the HR diagram it will fall. So the answer is, we don't precisely know. Given what we see on the surface, that say, for example, we see carbon on the surface, carbon compounds, we're pretty confident that it's at the helium stage, and since in the helium stage you will be burning some carbon, that you have dredged up some carbon on those surfaces, and we're seeing some of that. But we're not really seeing a whole lot of the other elements, so we don't really think it has been at that stage yet. But sooner or later, it's going to hit that silicon stage, and then the star is going to go through the steps that Dr. Field showed you, and it's going to blow up. So I'm going to go back for just a minute, going back to this shell. Remember what Dr. Field told you, that the core collapse can take place literally in fractions of a second, and then the star blow up. We will not know immediately that the star has blown up. We have to do that indirectly, because between the time that explosion actually occurs and the breakout shock reaches the surface, we're actually talking about a day. But there's a couple of things that will happen before we see that breakout shock occur. And that's the first, and there are two things we'll be looking for. Remember what Dr. Fields was talking about, that the collapse produced a ton of neutrinos? And we actually saw this in the supernova in the Magellanic Cloud back in the 1980s. Got these big, huge tanks, and basically one of the elements that a neutrino will occasionally interact with is chlorine. So kind of think of, well, you know what? You've got these tanks filled with basically bleach, basically filled with chlorine. And so we'll be looking for a burst of neutrinos from that supernova explosion. The other thing that we'll be looking at, and this was covered in a lecture I attended in Santa Barbara a couple of months ago, is that our actually best thing for seeing when it actually occurs is because of the density of that core. When that core collapses, it will emit what's called a gravity burst of waves. This is the expected waveform that we will see from LIGO. It's actually a very distinctive, and it's kind of the opposite of what we see from merging neutron stars. This is a signature that you can't miss. And you want to hear one of the great ironies? Back in January, LIGO detected something similar to this. It didn't look exactly like that, but it did look similar. And even more, gave everybody a scare. Guess what constellation LIGO saw this in? Saw it in the constellation of Orion. But when you actually, so we kind of thought, oh, did Betelgeuse actually blow up? No, it's still there. This was in a location fairly near. So that is basically the current estimate of where we are with Betelgeuse. I want to thank you all very much.
Wow, thank you, Dave. That was awesome. Thank you for taking the time to put that presentation together. That was really, really cool. Thank you. If you have any questions for Dave, you can always send me an email, aurora@centralcoastastronomy.org, and I can pass that information along to Dave, and he'd be happy to answer. Yes? Is that right? You would be happy to answer, Dave?
I'll be happy to answer.
Okay, great. Well, thank you so much. Yay! All right, everyone. I just want to give a shout out, thank you out to both Dave Majors and Dr. Bob Field. There are two last little tidbits I want to just show you really quick. The first one is that we have our next meeting is planned to be online. I will send you an email about it. You can find information about that on our website, and you will see that we will be having a representative from the Cal Poly Light Sail as our guest speaker for April. And the last thing is, now last weekend, Kent Wallace and I actually did a stargazing event where we did a planetarium-style star show with you. And if you missed that, you can take a look at it here. Something that I forgot to mention here, you just click play and this is the whole presentation. We recorded it so you could watch it anytime. One thing I forgot to say is you can also download the current sky chart. Now in last week's stargazing, we focused on objects that you were able to see either naked eye or binoculars. We actually went a little crazy near the end and started doing deep sky stuff. But if you would like a sky chart, they're free. And you can simply click on that link. It's at skymaps.com. And you can download your own personal sky map for the northern hemisphere, unless of course you're in Australia and you're watching us, then you're going to want something different. But I just wanted to make sure you knew that resource was out there as well. Okay, so we actually need to wrap it up. Oh, here's the sky map that you can download for free. Okay, so we need to wrap it up. Thank you so much. We had over 200 people attend this event, so yay! And again, if you have any questions or if you want to give us feedback, we would love to hear from you. You can just go to centralcoastastronomy.org, and we will get on our email list. Just send me an email, and we'd be happy to add you to our list. We'll let you know when our next events are coming up and what format they're going to take and how you can attend. But thank you, everyone, and have a great evening tonight. Take care.